Alright guys, quick video here on scientific method and experimental design. The scientific method is something we're going to use a lot in science class, and use it just in science in general as a really structured approach to addressing questions that we have. We call those questions problems. So in science we call it the question that we have, we call it a problem, and the scientific method is an approach that we can take to solving those questions. And we have very specific labels that we give to each step of this process. So this is what the scientific method would look like. It is, it starts off with the problem that we're going to be asking here, and then after we get our problem, we come up with a hypothesis or a prediction as to what we think is going to happen. Then we go through our experiment. So we come up with an experiment, we conduct our experiment, and with our experiment we have our results. We need to then analyze those results, and this is a really, really key important piece, is really analyzing the results. What do the results show us? What do the results really mean? And this is taking a good close look at the data, any graphs or things like that you make, and then you're going to come up with a conclusion where you are communicating to whoever the reader of your conclusion is, the audience there, what you found. So this is, what was the problem that you were addressing? What was your prediction, your hypothesis? What did you find to be the case after completing your experimentation? What is that? How did you conduct your experiment? What does the data show? And what does that mean about your hypothesis and about the problem? And then you should also indicate if any further research needs to be done. A lot of times the findings from an experiment may not be what you thought they were going to be. Your hypothesis isn't actually supported, so you need to come up with some new research. Maybe you have a new hypothesis or a new experiment because your experiment didn't actually do or didn't actually answer the question that you were trying to answer, so you need to come up with a new experiment. So really what we're looking at is the problem itself. This is just written in a very specific format as what is the effect of the independent variable on the dependent variable. So an example of this would be what is the effect of the height at which a ball is dropped on how high the ball will bounce. Notice I never said it, I never said I or we. These are pronouns. We don't want to use pronouns. Basically anything that has a specific scientific format should not be utilizing pronouns. In scientific writing, we really avoid the use of pronouns as a whole. Instead, we take a much more passive tone in our writing, where we're saying this is what happened, not I did this. So it's kind of just something to keep in mind. The IV, or the independent variable, that's what we are testing. There's only ever one. So in the case of this example, it's the height at which the ball is dropped. That's what I'm controlling. I'm controlling how high the ball is dropped from. And then DV, this is what we measure, or what happened as a result of any changes to the IV. So this, in the case of this example, this would be how high the ball bounces. That's what I'm measuring. After I drop the ball, I measure how high it bounced. That's what I think is going to be affected by my change of the height that I drop from. So that's our dependent variable. So after we come up with our problem, and our problem is written in this very specific format, we then come up with our hypothesis. The hypothesis also is a very specific format. It's really a prediction, and it's written in this: if this change happens to the independent variable, then this change is going to happen to the dependent variable. So going back to the example, a prediction for the ball dropping might be if the height at which the ball is dropped increases, then the height at which the ball bounces will increase. Again, because it's a very specific scientific format, we don't want to use any pronouns. So I'm not saying my hypothesis is this. I'm not saying if I do that or if you do this. Just if the ball is dropped from an increased height, then the height at which the ball bounces will increase. There's no pronouns listed there. After we come up with our hypothesis, we can get into our experimental design. This is actually designing our experiment. We need to make sure we specify our independent and dependent variables, and we have a control group. The control group is the group that we're always going to compare things back to. So if I'm looking at the example experiment that we were talking about, this might be if my starting height for the tennis ball was 50 centimeters, then that would be my control group. And the other height is going to be compared back to the height of 50 centimeters. So I might have the 50 centimeter and then a 70 centimeter and an 80 centimeter and a 90 centimeter, but all of the heights get compared back to that 50 centimeter group. That's my control group. The experimental groups are all of the other groups that exist. So these are ones that have a change to the independent variable. Next, we can look at the materials. We want to specify what stuff needs to be used when we conduct this lab. So the reader should know, or the person who's conducting a lab should know just from a list of materials, what stuff do they all need to get out in order to complete the task. And then the procedure is written. And this is really just a step-by-step list of instructions to complete the experiment, kind of like a cookbook. First do this, then do this, next do this. Again, when you write this, you would not have any pronouns. No, I do this, or next you do this. This is done first, this is done next, this is done third, and so on. You should also specify important constants, and these are just the things that remain the same in the experiment. In the case of our tennis ball being dropped experiment, I better keep using the same tennis ball, or the same type of ball at least. I'm better be dropping that tennis ball onto the same surface. If sometimes I'm dropping it onto a concrete surface and sometimes I'm dropping on the grass, that surface might make a difference. So those are things that would need to stay the same. They are constants. The only thing that should ever be changing is the IV, what you're controlling, and the DV that you're measuring. You really shouldn't have any changes to anything else. And then you need to conduct a certain number of trials. 3 is a pretty good number. Sometimes you would do more than that, sometimes you do less than that. It also sometimes depends on the outcome of our trials. But the whole goal of doing multiple trials or conducting an experiment multiple times is to eliminate the error that can exist as a result of the conducting of that experiment. Oh, this is spelled incorrectly. I apologize. So after you've conducted your experiment multiple times, done multiple trials to eliminate the error, you've got your data collected, and your data can be in one of two types. You have quantitative data. This is numerical data. It just has a number it's related to it. You can remember quantitative with an N is numerical. Qualitative is descriptive data. We always want to get quantitative data whenever possible, but sometimes that's not possible. For instance, if your IV or your DV is a color or a shape or a type of material or a feel of material, then you can't really always associate a number with that. So then you would have qualitative data. All right. After that, you're going to look at your results, look at the data. You probably will have graphed your data, and you're going to identify what is the data showing you. What does the data mean? What trends did you see? When you make a change to the IV, what happened to the DV? And really, ultimately, remember, this whole experiment was done because you had a question or a problem in the beginning. What is the answer to that question, that problem? That's kind of the next thing you really need to be doing. And then it's time to start writing a conclusion. And your conclusion always relates back to the problem and the hypothesis that you had with an explanation of what you did in the experiment. It should be accurate and relatively comprehensive or relatively complete. You should be specifying whether your hypothesis was or was not supported. We should not be using this word proven. Right? We don't want to say proven. We don't want to say a hypothesis was correct or a hypothesis was wrong. The hypothesis was supported if the data is aligned with what you expected to have happen, or your hypothesis was not supported if the data shows something different than what you expected to have happen. So you want to be specifying whether the hypothesis was or was not supported, and then why it was or wasn't supported. And then ultimately, again, tie back to the question. What was the answer to the question? So when you're writing a conclusion, you want to make sure you specify what was the problem, what was your hypothesis, what did you do to collect data, what does your data show, was your hypothesis supported or not, what was the independent and dependent variable and the relationship between the two, And there's really three relationships we're going to find this year. A direct relationship, which means that the independent and dependent variable change in the same way. They both increase or they both decrease. You could have a inverse relationship, which means that the IV and the DV move in opposite directions. One increases while the other decreases. Or there's not a relationship. And then you want to make sure you answer what the answer to the problem was. You want to provide that answer. So again, it's really important that we don't use pronouns. Your entire conclusion should be written without any pronouns. So again, it's not my hypothesis, we did that, we asked this problem, just avoid those pronouns. This is what happened. It's that very, very passive tone that you're going to take when you are writing your conclusion. So the last thing to kind of really address here is if your hypothesis wasn't supported, that's perfectly fine. In fact, most of the time when scientists come up with a hypothesis, their hypothesis is not supported, but they still learn something. They learn that what they thought was not actually correct, and that they need to come up with a new hypothesis and test that new hypothesis. So we always gain information whenever an experiment is done, even if our hypothesis is not supported, and that is perfectly fine. We should never be going back after we've done an experiment and changing what our hypothesis is. That should never, ever happen. You can come up with a new hypothesis for a new experiment, but you don't go back and change what your prediction was to make it so that you can say that your hypothesis was supported. It's perfectly fine if your hypothesis was not. All right, so that's basic information on your scientific method and experimental design. Make sure you touch base with me if you have any questions.